All right, so I'll give a quick tutorial as usual, and then you can just try the problems that are similar to the ones that I did in this quick tutorial. Basically, they want you to be able to recognize reduced row echelon form. And we specifically, when we get to row echelon form, for most cases, I can solve or do whatever task they want me to do in linear algebra if I'm using a matrix to row echelon form. The one case that I do need specifically to go to reduced row echelon form is when I'm finding the inverse of a matrix, which we're going to start talking about in the next few weeks. So we have 3 row operations to change an augmented matrix which I'll denote the coefficient matrix equals that B vector into an equivalent simpler form known as REF, or even reduced row echelon form. We're allowed to do 3 row operations. They are: 1, we can interchange 2 rows. And we will denote this by row I is interchanged with row J. That's the notation I'm going to use. And then 2, you can replace a row with a multiple of that row. RJ with K times RJ for any non-zero multiple. And then 3 is the weird one. What does this look like? Row J will go to K times row J. And then the last one is the weird one at first, but it will be also extremely useful when we do determinant row operations, which look like row operations, but they're not quite the same thing. We can replace a row I, let's do row I, with that row added to a multiple of another row. Another row. So what is that going to look like in our notation? Row I will get replaced by row I plus K times row J. Those are the 3 row operations we're allowed to use. And now on top of this, they're saying, here's a linear system, find out what the size is, 3 by 3, etc. And then what we want to do is how many equations do I have and how many unknowns do I have? Once I have that, they want you to augment the matrix immediately. Once I have that augmented matrix, this guy, what I immediately want to now do is use these 3 row operations to put it in row echelon form or reduced row echelon form. What are those? So if we are given an augmented matrix A, B, then it is transformed to row echelon form, or REF, if what are the conditions we have to have? 1, we have to have 3 conditions to be in row echelon form. You have to go through them every time. Every time you do a step, you say, am I in row echelon form? And then you have to go through these 3 conditions for yourself. any row consisting of all zeros is placed below rows which have non-zero entries. Two, so that's the easy one. Put 0 rows at the bottom is what that says. Put 0 rows at the bottom. 2, any non-zero row I don't think you have to do this for row echelon form, but for reduced row echelon form, it's a good idea anyways. So technically some books, and I'll show you what I mean in this case. Should I do that? I want to make it a leading one, but you want to have any row consisting let me put it this way. Has a leading entry. You don't have to have a leading one, is what I was worried about. Some books say you want to have a leading one. It's a good idea to make a leading one. I'll show you why, but a leading entry and must have zeros below the leading entry. Often leading ones, I'll put. And then 3, which is the weirdest one. So basically, you put 0 rows at the bottom. If you have rows that have leading entries or leading ones, you have to have zeros below those leading ones. And then the final condition is you have to have a staircase, basically, or you're supposed to do it backwards, basically, so that you can see it in the video. But it's going to be a diagonal staircase, which has this weird description in English. Basically, any 2 non-zero rows, the leading entry on the left, stage left, has to be farther to the right than the row below it. What? So in any 2, I didn't say it right, in any 2 non-zero rows, the leading entry in the upper row, so the row above, must be farther to the left than the leading entry in the lower row. This is row echelon form. What they mean by that is eventually you're going to have this staircase. So I like to have ones, but you can have 0, 3 equals 2, say, and then you can have 0, 0, 1, 2. And then, so if you have this, what they want you to see is the leading entry in, I have 2 non-zero rows. This is an REF definitely, because I have a 0 row, it's at the 0 rows at the bottom. And if you have a 0 row in row echelon form and you don't have contradictions above that says you have infinitely many solutions, the variable with no leading entry will be the free variable. So you immediately can know that x2 is going to be the t variable in this case. And then what are our other conditions? 0 rows at the bottom. If I have any leading or non-zero rows, then the leading entries have zeros below them, which I have in this case. I have zeros below this one, and I have zeros below this. So that's the condition that works. And then finally, I want to have in any two non-zero rows, in this case, I just have two non-zero rows. In the upper row, I have that the leading one is farther to the left than the leading one in the second row. And that's what they want. And then eventually you're going to get this staircase. And the staircase can look slightly different. In another case, if I have 1, 4, 3, 2, and then I have 0, 1, 2, 7, and then I have 0, 0, 1, 3, then I'm going to have a staircase, which is, this is going to be a unique solution. And this is definitely an REF. And so how do I tell in this case, if I have x1, x2, x3, if I have the same number of leading ones as I do variables that I had originally, I have a unique solution. And then the final case in REF for a 3 by 3 should look like this. If I have 1, 4, 3, 2, and then I have 0, 0, or sorry, even this I can have 0, 1, 2, 7. Then if I have 0, 0, 0, 1, or it doesn't matter what the number is, then this says 0, which is equal to 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 2. And that's bad because that says 0 equals 2, and this is a contradiction. Therefore, what's wrong? The assumption that this system had solutions was wrong. So we say, therefore, no solutions. And this is definitely REF. No solutions. Unique solution. Infinitely many. So this is why we want you to go to REF. Every time we go to REF, the game is, I can tell whether there's a unique solution, infinitely many solutions, or no solutions. And those are the only 3 cases we can have for a system for reduced row echelon form. Or RREF, we have to have a 4th condition. So 1, you want to be in row echelon form. And then 4, we have to have each column containing let's put it this way, I won't be confusing. All entries, all leading entries must be leading ones. And 5, we have to have all leading ones have zeros above and below them, have 0 entries above and below. So what's the difference? I'll go through one example and then I'll point out what happens when we do this. For a nice one, what we're going to get in the next one is we're going to get 1, 0, 0, 1, 2. So this is a reduced row echelon form. we still have this staircase. So go through the first ones, any non-zero rows, I have to go through the first three conditions. So you have to have this condition and this condition and this condition. And now you have to have two more, this condition and this condition. Once you're doing that, you have to go through the first ones. Any non-zero rows go to the bottom. I don't have any non-zero rows, so good, I don't have to check that condition. If I have any non-zero row, the leading entry, which it has to be a leading one, has to have zeros below it. So yes, 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 because the last one doesn't have any entries below it, so it has zeros below. The other ones have zeros all the way below. Then we say to ourselves, do I have the staircase? Yes. In any non-zero row, do I have that the leading entry in the upper row is farther to the left than the leading entry in the lower row? Yes. And then I go through the last two conditions. Are all my leading entries leading ones? Yes. And do I have that the leading entries have zeros above and below? Yes, in this case. Oh, that should be a 0. In this case, now you can see that I have leading entries above and leading zeros above and below the leading entries. Once I have this, eventually they'll call this upper and lower triangular or a diagonal matrix, the coefficient matrix, which happens to be the identity matrix. This just reads off the solution now. The unique solution has to be x is equal to 1, y is equal to 2, and z is equal to 3 if you use x, y, z, which was the one that I gave on the first practice questions, and I'll do that now. So where am I getting this from? Example. Where is this one? I'm going to use this guy. X plus y plus 2z equals 9. 2x plus 4y minus 3z equals 1. And 3x plus 6y minus 5z equals 0. Now, the solution I just showed is 1, 2, 3. This is the solution to this one. So as you're going, you want to work smart, not hard. You don't want to start introducing fractions right away. So the moves that I'm doing them so that I don't get fractions, because I know that the solution is integers in this case. And in general, I want to introduce fractions I want to avoid fractions for as long as I can. So I immediately augment the matrix. When I augment this matrix, I get 1, 1, 2, 9, 2, 4, negative 3, 1, 3, 6, negative 5, 0. What I now want to do is I want to do row 2. What we want to practice is getting a leading 1 and then eliminate below. Gaussian elimination means that we're going to eliminate variable x from the equation. We're going to kill this one and we're going to kill this one. How do we kill those? We want to do row 2 goes to row 2 minus 2 row 1, and row 3 goes to row 3 minus 3 row 1. When we do that, we get a new augmented matrix, which is equivalent because I'm using my row operations. And then what do I get? I get 1, 1, 2, 9. To get to REF, you never change row 1, so just copy it down. And then what I'm doing is I'm multiplying by negative 2. And so the whole point was to get 0. So when I multiply, I'm multiplying this by negative 2. So 2 minus 2 is 0. 4 minus 2 is 2. Negative 3 minus 4 is negative 7. And 1 minus 18 is negative 17. And then in the next one, now what I'm doing is I'm multiplying by negative 3. When I do that, I'm going to get 3 minus 3 is 0. 6 minus 3 is 3. Negative 5 minus 6 is negative 11. And 0 minus 27 is negative 27. this again, the solution is integers, and so I don't want to just divide by 2 or divide by 3 to get a leading 1. I want to get a leading 1 and then move on, but I'm going to do that by doing this. Row 2 goes to row 2 minus row 3. 2 minus 3 is -1, or I could replace this. You could do this slightly different ways, however you want to do this. But what I'm going to do now is I'm going to get 1, 1, 2, 9. And then now what I'm doing is, and I'm also not changing row 3 right now, so copy it down quickly. And then now I'm doing 2 minus 3 is -1. -7 minus -11 is 4, and -17 minus -27 is 10. Now what I want to do is, I want to do, first of all, I'm going to do row 2 goes to negative row 2, and then I'm going to interchange, no, and then I will do row 3 goes to, I'll do it one at a time, we'll go slow. So now we're going to multiply by -1. When I do that, I get 1, 1, 2, 9, 0, 1, -4, -10, 0, 3, -11, -27. Now, what I'm doing is I'm asking myself, in every case, do I have row echelon form? And in this case, no, because I still have this 3 to get rid of. So now I have a leading 1, I have a leading 1. And so what must I do? I have to get rid of that 3. So that says row 3 goes to row 3 minus 3 row 2 this time. I'm going to get a new equivalent augmented matrix. That augmented matrix is going to be 1, 1, 2, 9, 0, 1, -4, -10. And then I'm multiplying by -3 in this whole row. So I'm going to get 0, 3 minus 3 is 0, 11 minus, so -11 plus 12 is 1, and then -27 plus 30 is 3. This is a row echelon form. Why? We have the staircase. Any non-zero rows, which I don't have, are below any non-zero rows. Leading entries have zeros below them. And in any 2 non-zero rows, the upper row has a leading entry farther to the left than the lower one. So we get a staircase. This says we have a unique solution. From here, you can do back substitution. First of all, it says Z equals 3, and then 1 plus, or 1. This says y minus 4z equals -10. So y is equal to -10 plus 4 times z, which is -10 plus 4 times 3, which is 2. And then z, or sorry, x turns out to equal 1 from the last equation. So you get 1, y is 2, and z is 3 is the unique solution. Or you can keep going. If I keep going to reduced row echelon form, what I want to do now is I'm going to do row 1 goes to row 1 minus 2 row 3, and row 2, I'm going to change the other rows with row 3 now to get rid of these entries. And then, so this will be row 2 go plus 4 row 3. So 0, 0, 1, 3. I didn't change that one. And so now what I'm going to get is 1, 1, 0, 3, 0, 1, 0, 2. And then finally, I need to get rid of this entry. I'm still not in not, so this is not reduced row echelon form, but it is row echelon form. Here we're still not reduced row echelon form, what it is in REF. And so when I get rid of this last row, this will be row 1 goes to row 1 minus row 2. And we get exactly now this is reduced row echelon form. All 0 rows go to the bottom. If I have non-zero rows, they have zeros below them. If I have any 2 non-zero rows, the upper row has its entry, non-zero entry further to the left. And all my leading entries have to be leading ones, check. And they have to have zeros above them now. And that's exactly what I have. So this is a unique solution, and it just reads off the solution now. This just says x equals 1, y equals 2, z equals 3 is the new system that we got from that old system. So this is why the RREF system, it just reads off what the unique solution is when you're in reduced row echelon form. If you're in row echelon form, like here, then you're going to get a system that is simpler, and then you can use back substitution to find out what they are. One of the other ones I wanted to do, where's the other one? They give on the practice, they're going to give a lot of the time. So example 2, they'll a lot of the time put an A and a B in a question and ask you when you have a unique solution, no solution, or infinitely many solutions, and find all of the A's and B's, or find all the A's. And what they mean by that is they want you to put it into REF. Our REF usually isn't necessary, but in row echelon form, because of back substitution, I can always tell whether there's a unique solution, no solution, or infinitely many. And then that's the game that they're trying to play. So if I'm given the system x1 plus x2 plus x3 equals 4, x3 equals 2, it just tells me straight up, and then negative x1 minus x2 plus a squared minus 5, x3 equals a minus 6. Find a in R with 1 unique solution, 2 no solution, and then 3 infinitely many solutions. So I look at the augmented matrix immediately. The augmented matrix is going to be what? I'm going to have 1, 1, 1, 4, 0, 0, 1, 2, negative 1, negative 1, a squared minus 5, a minus 6. Is this an REF? No, because this leading entry has to have zeros below it. Therefore, I'm going to do row 3 goes to row 3. So what I'm trying to do is turn this into an REF, and then once you get close to an REF, there will be cases when you want to divide by a squared or something like this. And once you're dividing by your variable, this is when I'm going to get conditions, because you don't want to divide by 0, but you want to get to REF. So what I'm trying to do is carefully use the third row operation, which is the safest, to manipulate. And so I'm going to do row 3 plus row 1, and that will give me an equivalent system and get me closer to REF. And then we'll see what happens. What happens in this case is I'm going to get 1, 1, 1, 4, 0, 0, 1, 2. So we already know that x3 is 2, but now we're going to get 1 plus 1 is 0. 1 plus 1 is 0. A squared minus 5 plus 1 is a squared minus 4. And then a minus 6 plus 4 is a minus 2. And then I can write this as, let me give myself some more space actually. So that's what I'm going to get at. A squared minus 4 is a perfect square, so I can split this. Now, what I want to do is I want to divide by a squared minus 4 to get a leading 1. But to do that, I'm dividing by 0 sometimes, so you get cases. Either equals 0, it's either not equal to 0, or a squared minus 4 is equal to 0. So if it's not equal to 0, that says a does not equal plus or minus 2, or a equals plus or minus 2. So I have 3 cases. 1, or let's do it like this. 1, a is not equal to plus or minus 2, then I could have where a equals positive 2, and then 3, a is equal to negative 2. Those are the 3 cases I have to go through. And then I'll probably get one that has a unique solution, no solution, infinitely many solutions. So in case 1, if a does not equal plus or minus 2, then a squared minus 4, which is a plus 2, a minus 2, doesn't equal 0. So I can divide by this, and we are going to get an augmented matrix that looks like 1, 1, 1, 4, 0, 0, 1, 2. And now I can do 0, 0, 1, 1 over a plus 2. So is this an RAF? No. So what do I want to do? You look at this. I was just going to draw my staircase, but then you don't get that. So I have now a leading entry, and a leading entry, I have to get rid of this below. So what I'm going to do is I'm going to do row 3 goes to row 3 minus row 2. That gives me a new augmented matrix 1, 1, 1, 4, 0, 0, 1, 2, 0, 0, 0. And then what we're going to get is 1 over a plus 2 minus 4, or sorry, minus 2. The point is, in this case, what do we get? 0 equals 1 minus a plus 2 minus 2. You have to multiply by a plus 2. And that is definitely non-zero, this thing. Because a plus 2 is non-zero, because it's not equal to plus or minus 2. So this gives us a contradiction. So no solution. So in any case where a is not equal to plus or minus 2, there's no solution. What about if we do case 2? A was equal to positive 2, then this says a squared minus 4 is equal to 0, but a plus minus 2 or and is 2 minus 2 is equal to 0. So we get the augmented matrix 1, 1, 1, 4, 0, 0, 1, 2, 0, 0, 0, 0. This is an REF. And so we have infinitely many solutions. And then in case 3, we have a is equal to negative 2. This says that a squared minus 4 is equal to 0, but negative 2 minus 2 is not equal to 0. So this is a minus 2. So we get the augmented matrix 1, 1, 1, 4, 0, 0, 1, 2. But now finally this time we get 0, 0, or we didn't get one of the cases in this one strange one. We get 0 and then negative 4 So 0 does not equal -4. Contradiction. So no solutions. So one, unique solution. Never. Two, no solution. As long as A does not equal -2, we get no solution. And three, sorry, +2. If A is equal to 2, we get infinitely many solutions. And then so that just classifies for every value of A in this type of game, whether we get one solution, no solution, or infinite many solutions. Getting to row echelon form or reduced echelon form has many applications. We're going to use a row echelon form to find inverses of matrices. And then we're going to also use row echelon form to determine whether we have spanning sets or linearly independent sets of vectors or basis vectors in dimensional spaces. And then so we're going to answer these more sophisticated questions using the row echelon form or reduced row echelon form of the matrices. So this game of finding the A's is making you do this mantra of make sure it's in row echelon form, or reduced row echelon form is fine as well, but REF will do it for most things. And determining whether I have one solution, no solution, or infinitely many solutions always comes from assessing what cases I have in these A's and B's, and then looking at the augmented matrix in that case. And if it's in REF, then I have to be able to recognize whether I have one solution, no solution, infinitely many solutions based on the first non-zero rows. Choose infinitely many solutions because as soon as I have a row of zeros, where is it? In case 2, I have, so specifically for, let's do it here. And then we can look at what the solution is. 2, if I have 1, 1, 1, 4, and then I have 0, 0, 1, 2, and then I have a row of zeros. This row of zeros tells me immediately I have infinitely many solutions. Again, do I have a staircase? Yes, I do. Which have leading entries, these guys. So x1 and x3 we can solve for, but x2 has no leading entry in the column. This will be the free variable. So x2 is going to be free. So how do I start solving for this? Well, this row tells me that 1 times x3 equals 2, or x3 is just equal to 2. So I've already got him. Then from what I just said, we're going to say that we know that x1 plus x2 plus x3 equals 4. That means that x1 is equal to 4 minus x3 minus x2. This shows me that I have too many variables, so one of them has to be free. And we already know what x3 is. This is 4 minus 2 minus x2, which is 2 minus x2. So we let x2 equal t be free, which we already knew from here anyways. And then this says that x1 is equal to 2 minus t. Therefore, we have infinite and many solutions of the form x1 equals 2 minus t, x2 equals t, and x3 was equal to 2. If you want to write this in vector form, we're going to get x1, x2, x3 equals, where's the constant vector? I have a 2, and then I have no constant in variable 2, and then I have a 2 in that one, and then I can have plus t times the scalar multiple of, what do I have in the first one? -1, and then I have 1, then I have 0. this is eventually the vector v in the direction, and this is the point p naught. And what do you need? You need this vector x to equal p plus tv. And so this is a line through p naught in the direction of v in 3 space. So just like we were doing it in the plane now, what this says is as soon as you have infinitely many solutions, every row of 0 is going to give you a free parameter, and that will tell you that you have every time you have a free parameter, that gives you a dimension of the subspace that is going to be that solution. And so this says that every point on this line through 2, 0, 2 and in the direction of -1, 0, 1 will be a solution to that system, to that 3x3 system. And so this is a one-dimensional line in 3 space. Every point on that line in 3 space is a solution to the system of your 3 equations. Oh, the battery on my pen is dying. So that seems like a good time. Again, what's -2 minus 2? I'm assuming you have to keep, this is what you have to be trained to do, is I'm saying A is equal to -2. So what's -2 minus 2? -4. Yeah. And so in each case, but in that also in this infinitely many cases, we have they're going to ask for the geometric interpretation, et cetera, et cetera. So in this equation now, in this system, if I had, this was the RAF of my system in case 2, then I have from this scenario, the fact that every point on this line in 3 space is a solution to this system of 3 equations. If you had 2 rows of zeros, now what? Is this reduced row echelon form? Yes, but this is REF, which is close enough. I still have my staircase, but this is weird. This says I'm going to have 2 variables. Where's my leading entry? My leading entry is right here. So x1 is going to be the thing I can solve for, but these guys don't have leading entry, so they're going to be free. So x2 is going to be s and x3 is going to be t, are both free in this case. And so in this case, from that single equation that we have, x1 is equal to 4 minus x2 minus x3. But now we're saying this says x1 is equal to 4 minus s minus t, x2 is equal to s, and x3 is equal to t. This is our infinitely many solutions. S and t are now both real numbers. This is our solution set. And then finally, as vectors, this will be x1, x2, x3. And then what do I have? I have the point 4, 0, 0. And then I have plus s times the vector -1, 1, 0. And then plus t times the vector -1, 0, 1. And then now I have point p naught, and then I have 2 vectors u and v. And then our equation is x is going to equal p naught plus s times u plus t times v. And then because I have 2 vectors, this is a plane in 3 space. Every point on that plane now is a solution to that linear system. So that's what they mean by the geometric interpretation. I'll digress there and then have a good weekend. If you have any other questions about the problems, this is what the games that they're playing. So have a good weekend. I'll see you next Thursday.